A wave on a string is described by the equation y of position and time is 0.25 times the sine of 3.14x plus 450t, where all the numbers are in proper MKS units. Then follows a series of questions. The key to solving this problem is demonstrating a thorough understanding of the equation that governs this wave traveling on a string. The equation says that the string will be displaced in the y direction differently at different locations and at different times. We've decided that this will be a sinusoidal kind of a wave, so there will certainly be a sine function involved. And we recognize several things. Number one, we recognize that the string will be oscillating with some sort of an amplitude. In the case of a string, this amplitude will be a number in meters that tells the height of the wave itself. If this were another kind of a wave, for example, a pressure wave of sound in air, then the amplitude would be in pascals, saying how much above and below normal air pressure the wave represented. This wave will also be a function of position and time. We remember from the case of simple harmonic motion that there is no such thing as the sine, cosine, or tangent for that matter of a time interval. Therefore, we required that any variable t be preceded by a unit conversion which we called omega. The purpose of omega was to cancel away the unit of the t variable, which was seconds, and leave behind an appropriate angle, the natural angle unit is radians, so that we could proceed to take the sine of this result. In order to make a proper unit conversion, we recognize that one full cycle can be represented by 2 pi radians, and it can be represented by tau seconds, where tau is the period, so that omega is 2 pi over the period, just as simple harmonic motion, or is 2 pi times the frequency. This means that we have a set of synonymous variables, omega, period, and frequency, knowing any one of them, and you know all three. A similar trouble exists when we try to write a wave as a function of position. There is no such thing as the sine of 3 meters. It must be an angle. Therefore, a factor which we call k, it is not the spring constant, but it is known as the wave number, is applied to convert units just the way omega did for the time intervals. We clearly need to eliminate the unit meter that came from x and leave behind the unit of radians. Just as before, we recognize that a single cycle is 2 pi radians, and the amount of distance represented by a single cycle of a wave is lambda, known as the wavelength of the wave. Finally, the last aspect of a standard sinusoidal traveling wave formula is that the factor between kx and omega t is written as minus or plus, meaning that both a minus and a plus are a proper solution. The reason we use minus or plus rather than plus or minus actually is to encode a hint or reminder to ourselves. This reminder indicates that something is backwards with regard to our thinking. The thing that is backwards is the direction in which the wave travels. If we use a minus sign, this is indicating that the wave travels towards plus x. And if we use a plus sign, this indicates that the wave travels towards minus x. Armed with this understanding, we can recognize what the 3 numbers we've given in the original equation represent. These numbers are 0.25, 3.14, and 450. Since the 0.25 multiplies the sine function, we recognize immediately that that is the amplitude of the motion, and therefore is in meters. Since the 3.14 multiplies x, we recognize that is the wave number k, and the wave number k is in radians per meter. Finally, we recognize that the 450 multiplies t and is therefore the appropriate unit conversion, 450 rad per second. Using this information, we'll actually find that the problem is quite easy to solve. Part A asks for the frequency of the wave. Frequency, period, and omega are synonymous variables. If you have any one, you have all three. And clearly, since omega was 450, we can immediately set this equal to 2 pi times the frequency to solve for a frequency of 71.62 Hertz. Part B asks us for the period, that is the other synonymous variable of our set omega period and frequency, so we can get to the period by taking 1 over the frequency with the result 0.014 seconds. Part C asks us to find the wavelength of the wave. Well, wavelength is the synonymous variable to wave number, and since we know that the wave number k was given by 3.14 radians per meter, we'll be able to find the wavelength by recognizing that k is always synonymous with wavelength, since k is 2 pi divided by the wavelength. Rearranging this algebraically, we get the result that lambda is equal to 0.50 meters. Part D asks us for the velocity of the wave. Although I have always felt that it is most obvious to recognize that every wave travels one wavelength every period, so that distance over time is velocity, most students find it easiest to remember that velocity is wavelength times frequency. Since we've solved for these in previous parts of the problem, we can simply plug them in to get the result that the velocity of our traveling wave is 35.8 meter per second. In Part E, we're asked for the amplitude of the wave, and we already decided that the amplitude is the factor that precedes the sine function itself, meaning that it is 0.25, and in MKS units with a traveling wave on a string, the appropriate units are meters. Part F asks whether the wave is traveling in the positive or negative direction, and we remember that since the formula says that it should be kx minus or plus omega t, it travels in the direction opposite to the sign between the kx and the omega t. Since it was a plus in this problem, we recognize that our wave is traveling in the negative x direction. Finally, we were asked that if the tension in the string were 100 newtons, what will be the mass density mu of the string? This part of the problem refers back to the fact that for every wave, the physical quantity that distinguishes the situation at hand is the velocity with which that wave travels. And we have a variety of formulas depending upon what is the physical situation at hand. If we have waves traveling on a string, then the velocity of these waves is the square root of the tension in this string divided by the factor mu, where mu is the mass per unit length of the string itself. If we have waves traveling in a bulk medium, which is denoted by a bulk modulus, capital B, then the velocity of waves in this string will be capital B, the bulk modulus in pascals, divided by the density of the medium itself. If we have a tensile compressional wave, this is the wave that you get if you hammer the end of a long rod, then in this case it's very similar to the previous formula in that we have the Young's modulus, or the tensile modulus, divided by the density. Finally, if the material is air, we recognize that under standard conditions of temperature and pressure, we have a fixed value. Temperature and pressure actually varies a lot. I like to use the number 345 meter per second simply because that's easy to remember. Your book may use 344, 342, but something in this ballpark of 345 meter per second is the velocity of sound in air. For the problem at hand, we'll be solving the situation of waves on a string. Therefore, we'll be able to take the velocity that we solved for in the previous part of the problem and set it equal to the square root of tension divided by mass per unit length, as shown here. 35.8 meter per second equals square root of the tension of 100 newtons divided by the mass per unit length, and this leads us very simply to the solution that the mass per unit length is equal to 0.078 kilograms per meter.